What we're going to do in this lesson is something called implicit differentiation. So far, everything that we've done the derivative of we don't call it explicit differentiation, but that's really what it is. For example, let's say I have y equals x squared plus 3x. So we would say, oh, well, what's the derivative of that? So what we're really saying is, what's the derivative of that with respect to x? So remember how sometimes I would write y prime, and then other times I would write dy dx? And I said, well, I really like the dy dx, and some of you think, well, y prime is easier to write, but let me just show you. What we're actually doing is we're saying, take the derivative of both sides. Even though I never show that left side, I'm saying take the derivative of y with respect to x. Well, what is that? That's just dy dx. Think of it as almost like multiplying in a way, even though technically that's not what we're doing, because this is taking the derivative of y. What's the derivative of y? We don't know. That's the derivative of y. We're going to figure out what that is by differentiating the right side. So what's the derivative on the right side? Yeah. Now, 2x plus 3. So what we encounter with implicit differentiation is sometimes we don't have just y equals. Sometimes y is part of the equation. So in this case, we have x squared plus y squared equals 9, which is a circle. But could I still find the slope? Yeah, I mean, I could find the slope here, right? I could find the slope here. The only two places I can't find are here and here because it would be undefined. So dy dx. So undefined at those two locations, but everywhere else I do have a slope. Right, I could see here the slope's going to be 0. It's also going to be 0 here. And then I can see there's going to have a positive slope. Down here it's going to have a negative slope. So it's going to depend on not just our x coordinate, but also our y coordinate in this lesson. Okay, so far when we've done the derivative, all we've ever done was plug in an x value. But now I'm going to have an x and a y. Does that make sense? So I'm going to get a formula for dy dx with x and y kind of mixed into the equation. Okay, so here's what we're going to do. Notice how I wrote up here, we did d dx of both sides. That's what we do in implicit differentiation. So I'm going to write d dx of x squared plus y squared equals d dx of 9. So whatever we do to one side of the equation, we have to do to the right side. Now again, just so you know, we've been doing this all along. We don't necessarily write it out in that step. We have been doing the derivative of both sides. Yeah, I just wanted to show that top part. Okay, so far, haven't done anything spectacular, okay? Now we're going to take the derivative of the left side. Now the derivative of x squared, we just do the derivative like normal. That's going to be 2x. Plus, all right, now, what do you think would be the derivative of y squared? 2y. That is the first part. Chain rule, dy dx. So y is some function of x. Think of this as, and I'll just go through a couple quick examples so you guys can see. So when I have y squared, right, and I want to find the derivative of this, we think of y is inside. We don't know what y, could I isolate y in this equation? Yeah, but then you'd have like a plus or a minus and a square root, right? It doesn't come out to something nice that we can differentiate. So that's why we want to, whenever we have like a y squared or a y to the third or a cosine of y, we can't isolate the y very easily. So this is where we need to use implicit differentiation. So when I do the derivative of this, remember it's chain rule. So derivative of the outside, keep the inside the same, that's our y, times the derivative of the inside. Okay? It's really just chain rule. That's all implicit differentiation is. Now, let me just show you. No, what's the derivative of y squared? Think of what's the derivative of x squared? 2x. So every time we do implicit differentiation and it's not an x, you're going to have a dy dx or a dw. So let me give you some examples. Let's say I do the derivative of sine of z. So it's going to be cosine of z dz dx.
It's not the derivative of just y.
So if I have, so let's say it's w to the third, it's going to be 3w squared dw dx. Because, but w to the third, imagine if that was x to the third, what would be the derivative? It would be 3x squared. So we have 3w squared, but this isn't an x. Let me explain it to you this way. Let's say it was x cubed. We'd have 3x squared dx dx. So I could actually think of the x's as then I would have dx dx, but what's dx over dx? That's just 1. They cancel each other out. So whenever we encounter x, we just differentiate like normal. Whenever it's something that's not an x, we're still going to differentiate like we would normally, but then we always have to multiply at the end by d whatever that variable is over dx. So if I have dx of tangent of theta, what would that be? So it would be secant squared of theta d theta dx. Okay? When we get to chapter 4, it will. But for now, you just need to remember to leave it that way. Okay? So, now, if it doesn't make sense to you and you still don't see where the chain rule is, just kind of memorize this is what you have to do. I hate to say that. Like, maybe eventually down the road it will click. In chapter 4, when we get to that second semester, you have to understand the implicit differentiation to do the applications, because what we'll do in chapter 4 is we're going to take the derivative with respect to time. Yeah, so that's where we actually apply this concept. Does that make sense? Okay, now on the right side, d dx of 9, what's the derivative of constant? It's still 0. Now remember, my entire goal here is to find dy dx. Right? That's what we're trying to find. Well, I have dy dx in my equation, so now I want to isolate that. Okay, so I have 2x plus 2y dy dx equals 0. So I'm going to subtract 2x from both sides. So I have 2y dy dx equals negative 2x. And then I want to just divide both sides by 2y. So I get dy dx equals negative x over y. So that means if I know the coordinates for x and y, I can find the slope. Okay? Makes sense? So now on that circle, if I gave you the point, well, it'd be like 1 and then like 2 root 2, because it's x squared plus y squared equals 9. So if I gave you those points, you could find the slope at different points on the circle by just plugging both of them in. Yeah. So if I said, oh, what's the point 1 comma 2 root 2, which is not a pretty point, but could you find the slope there? Yeah, dy dx evaluated at, so it would be negative 1 over 2 root 2. That would be the slope at that point. Okay, that's just an example. All right, example 1, we want to find dy dx if y squared equals x. Again, I'm going to leave oops. So I'm not going to try to isolate y. If you can easily isolate y and then do derivative like we had originally learned, then that's fine. But here, again, when I take the square root of both sides, I have a plus or a minus. It just gets real messy. So also, what does this graph look like? Y squared? Like a sideways parabola? Yeah, y squared. Instead of x squared, it's a y squared, so it opens up to the right. Don't worry, you don't need to know the graphs of these. You just need to be able to do the implicit differentiation and then plug in. So we want to find the slope at the point 4, 2, and 4, negative 2. So about like here, that slope and this slope. Okay, what do we get on the left side? 2y dy dx. And what do we get on the right side? Just 1, right? Derivative of x is 1. So dy dx equals 1 over 2y. So notice it doesn't even depend on the value of x now. It only depends on the value of y. However, when I write out dy dx, I am going to put evaluated at 4, 2. So what do we get? 1, 4. And what do we get for dy dx evaluated at 4, negative 2? Negative 1/4. Oh, we could look at the graph and we can kind of confirm that from geometrical standpoint. So here, it looks like a slope of 1/4. Notice down here, that is a slope that is negative. Okay, any questions? Good? Not that bad. Okay, so example 2. Example 2 is just like the very first one that I walked you through. So go ahead and see if you can find the slope of a circle, x squared plus y squared equals 25, and then find it at the point 3, negative 4. So if you get stuck, just look back at the front page because it's going to look very similar.
So I get confused because sometimes it's dy over dx and sometimes it's d over dx. So is that x
Okay.
squared plus y squared like y?
Okay, so the d dx is just, that's what I'm doing to both sides. So I'm saying, whenever I see d dx, it means, okay, I'm going to take the derivative of whatever with respect to x. So you could have like lots of terms. Everywhere I encounter x, I just do the derivative like normal. Anytime I encounter something that doesn't have an x in it, has a y, has a z, has a, b, c, it doesn't matter, I'm going to have to put the d, whatever the variable is, over dx. So here I get 2x. What do you get when you take the derivative of y squared? 2y dy dx.
Does it matter if you put d over dx or dy over dx?
It does. You need whatever you're taking the variable of, that's what you need. So
No, I get it. I get it.
are you sure? I was just gonna so like if I do d dx and I have y to the third minus w to the fourth plus 4a. Let's just say I do the derivative of that. So I get a 3y dy dx minus, 4w to the third dw dx plus 4 dA dx. So whatever variable you're working with, that then is what I'm taking the derivative of with respect to x. Because each time, like here we think, oh, my y is my inside. So it's the derivative of the outside, keep the inside the same, times the derivative of the inside, so dy dx. Here, derivative of the outside, keep the inside the same, times the derivative of the inside, where it's w this time. Does that make sense? How each part you have to treat differently with respect to x. Okay, so now back to this. Not back to this yet. Are we okay on this? Yeah, it's still a little. There's tissues right here. Don't cry.
Oh no, it's just winter.
Like explain it like just with words.
So
Words.
with words. I don't know how else to.
Like the reason why you do it.
Okay. Let's say I have some crazy cosine of y plus y to the third minus sine of y squared is equal to x. Now, the only thing that's easy for me to differentiate here is the x. In each of these, the y is some function of x. In other words, in some mathematical world, I might be able to isolate the y, just not in our world.
In your world.
Or in my world. But this is a function in terms of just x and y. So right now I have it as x equals, but maybe some way in some math world we could actually isolate the y. But in this case we can't. So we treat y as the inside. And we do the chain rule. So derivative of the outside, keep the inside the same times the derivative of the inside. Plus, now we have derivative of the outside, keep the inside the same, times the derivative of the inside. It's just chain rule. That's all it is. It's chain rule. Minus, and now we have cosine, keep the inside the same, times the derivative of the inside. So that's actually chain rule twice. And then this whole thing equals 1. Exactly. We don't. Well, not only do we not know what dy dx is, but the whole point to this is that that's what we're trying to find. Now we have a whole bunch of dy dx's. We'll get to that in the next problem, how to isolate that. Okay. Are we okay getting 0 on the right side? All right. So what do we notice? We get the same answer as we had on the previous page. So tell me, any kind of circle that has a center at 0, 0, won't that have a slope of negative x over y? Every single time, because no matter what the radius is, when you do the derivative of the radius squared, you always get 0. So you're always going to get negative x over y. Now, we want to find at the point 3, negative 4. So we have negative 3 over negative 4. So 3/4. Okay. All right, example 3. Show the slope dy dx is defined at every point on the graph of, we have 2y equals x squared plus sine y. So first thing, I'm going to just do dx of both sides. Okay, what would the derivative of 2y give us? 2. And then what? Dy dx. Okay there? On the right side, what's the derivative of x squared? 2x. Plus Now the derivative of, okay, so it's going to be cosine of y dy dx. Now, it's always times dy dx, always times. Now I have dy dx on both sides. So imagine if this was a variable. Let's say, it was 2a here, and then a cosine of y times a. What would you do when you have variables on opposite sides? You want to get everything on one side. So I'm going to move this to the other side. So I have 2 dy dx minus cosine of y dy dx equal to 2x. I did the derivative.
Because you did cos of y, you don't do the inside.
But what's the derivative of y? Dy dx. Yeah. I know, it sounds weird to say, like, oh wait, didn't we do the derivative of y? But that's what dy dx is. Derivative of the outside, keep the inside the same, times the derivative of the inside. And our inside is y.
Oh.
So now what I want to do is factor out dy dx. So I get 2 minus cosine of y equals 2x. So dy dx is going to be 2x over 2 minus cosine of y. And don't try to cancel the 2's. There's a subtraction sign there. Okay, so that's my derivative. Now, that's pretty much all I would ask you, like on a quiz or a test in terms of something like this. I might actually have you plug it in. This question just says, show that the slope is defined. In other words, will the denominator ever be undefined? So it's defined because, what's cosine? Cosine has to stay between what values? Think on a graph though. Stays between -1 and 1. Right? So cosine of y must be in this range from -1 to 1. So will you ever get 0 in the denominator? No, it's impossible. Cosine of y could never be equal to 2. Right? It can only be in values between -1 and 1. Okay, so here is the implicit differentiation process. So just to kind of sum that up, what we did. So we differentiated both sides with respect to x. Then we had to collect dy dx on one side of the equation. Now, if you only have one dy dx, you don't have to worry about this step. But if you have multiple dy dx's, get all of those on one side. Anything that doesn't have a dy dx on the other side. Then you're going to factor out dy dx and then solve, which is usually dividing. Usually that last step is just divide, like we saw here. Right? After we factored, we just divided. Okay, let's try another example. Just keep in mind for this lesson, I'm going to try to get through all the notes, and then the next class is tomorrow. Do we meet tomorrow? No, Wednesday. So we'll have time to go over all the homework. This is a 2-day lesson, but I at least want to get through the notes. Yes. Okay. Let's see how far. How much time we have left in class, and I'll let you know. Okay, so we want. Don't worry if you didn't know this was the graph for an ellipse. I'm not going to have you graph them. But yeah, this is actually where conic sections are applied in calculus. They give you an ellipse or a hyperbola or something, and they say, well, find the slope of that. This is what implicit differentiation would be used for, because there are practical applications where you have a different kind of shape, and you want to be able to find the slope of those lines, like slope at different points. Okay, this one gets more complicated because of the x times y, which means it has a product rule inside. Okay, here, maybe over on the side, let's just look at this dy. Let's look at just taking the derivative of x times y. Before we actually tackle the problem, because this is what makes this one a little bit more difficult. Now, the product rule is what? Derivative of one, keep the other one the same, and then plus the other one. Okay, so do you want to take the derivative of x or y first? X. Okay, derivative of x is 1. Keep the second part the same. Okay, so derivative of x is 1, and then we keep the y. Okay? Now we're going to keep the x, but we're going to have derivative of y. Well, that's just dy dx. Are you okay with that? Product rule. Oh, yeah. So what's the derivative of y? It's 1 dy dx. I just didn't put a 1 in here. You don't need a 1. If you want to put it in 1, go for it. That's the derivative of y. I know it's just different for you guys because you've always had y equals x squared. So I would say, oh, well, what's the derivative? But when we did the derivative, we only took care of the x. But we really were doing dy dx the whole time. We were doing the derivative of y. It's just dy dx. It's kind of like the obvious thing that just sounds weird now that we're actually doing it in separate pieces. But we've been doing this all along. Every time I gave you a y equals something, you would write dy dx because you were saying the derivative of y is dy dx. I don't know. This is always one of those weird lessons that eventually, I think, after you practice it enough times, it kind of sinks in. But when you first see it, it's just different. Okay, so let's go through. What's the derivative of x squared? 2x. Minus, okay, the derivative of xy, we just did that whole thing over here, right? So I'm going to put it in parentheses though, so I remember to distribute the minus. So it's 1 times y plus x times dy dx. Yeah, I just copied it exactly the same just so you guys could see the steps. Okay, the derivative of y squared is going to be 2y, and then don't forget we need another dy dx because that was derivative with respect to x, right? And then equals, what's the derivative of 7? 0. So I have 2x minus y minus x dy dx plus 2y dy dx equals 0. What? Yeah, what do we want to move? Yeah, okay, so you have a choice. You can either move these two terms to this side or these two terms to this side. Doesn't matter. Pick one. Which one do we want to pick? Do we want to leave the dy dx on the, you want to move the dy dx to the right side? Okay, so I'm going to move these two over here. So I'm going to leave 2x minus y, and I'll have an x dy dx minus a 2y dy dx. Okay with that? Which part? Okay. I'm doing a screencast, so if you need to go back to some of these examples when we work on homework. What's the next step from here? Okay, I have 2 dy dx's, so I want to pull that out, and I'm left with an x minus 2y. So I've factored it out. I've done step 3. So now the last step is to solve. Again, usually divide. So I'm going to divide by that whole thing. So I have 2x minus y over x minus 2y. That's my slope. Okay, it's a little messy. It is. but that's my slope. So now, when I find my tangent and my normal to this curve, and I'm giving you the point -1, 2. So what do I need for the tangent? Yeah, I just need to find the slope. So let's find dy dx at -1, 2. What's that going to be? So I have 2 times -1 minus 2 over -1 minus 2 times 2. Four-fifths?
Yeah, but
Four-fifths? Okay, so what's the equation of my tangent line? So it's y minus 2 equals 4/5 x plus 1. Exactly. All I need to do for the normal, I've done all the work. I just need to take the negative reciprocal. So it's going to be y minus 2 equals -5/4 x plus 1. Okay, questions? Okay. So just like other derivatives where you can find the second and the third derivative, we could do that with implicit differentiation as well. So let's take this example. Let's find the first derivative, and then we're going to use that first derivative to find the second derivative. Okay. So we'll start with d dx, and don't have to worry about any product rule or anything here. Okay, go ahead and try, see if you can get the first derivative without any help. Oh, you can do it. Just remember, all the y's get a dy dx at the end. That's all you have to remember. Otherwise, everything looks the same from what we have done previously. Yeah, see if you can get all the way to dy dx equals. So you can get the whole thing. And reduce if you can. Because you're going to want this in as simple terms as possible, so that when you do the second derivative, it makes it a little easier. Okay, got it? You don't think you did it right? Okay. So, oh, you need another minute? You don't think you did it right? Okay, so we get 2y dy dx plus 2 dy dx equals 2. You got that step? Okay, we're going to take out a dy dx, so we get 2y plus 2. Yeah, in fact, when I reduce it, so I have 2 over 2y plus 2. Now, I can basically factor out a 2 out of the denominator and then cancel it, which is, yeah, you could have factored it out, but in the end, what I would like to see is just 1 over y plus 1. Yes. Yeah. Oh, y prime, yes. Yeah. Okay, so that's a good question. Sometimes I will even do this. Sometimes, you know how we used to write y prime? So another way to look at this is you could do 2y, y prime, plus 2, y prime, and then equals 2. Remember, y prime is the same thing as dy dx. The reason I write dy dx is when we get to chapter 4, you don't have that option anymore. It has to be like d something dt. So I guess that's why that's fine. So if you prefer to write y prime and then just switch it to dy dx at the end. Okay? All right. Yes.
So, for the derivatives of x, it's just like you just wrote 2, right? So you don't
Yeah,
have
because
nine.
just think of 2x. We just treat that normally.
Okay, we treat all the x's.
Yeah.
normally. Okay.
Okay. Now we want to do the second derivative. We just do it again. Okay, but this gets a little tricky, so I want to take this slow.
Chain roll, right? You bring it up.
Okay, so
Take the derivative of dy.
so this is just notation. This is the second derivative of y with respect to x. So it's kind of like saying, think about it like you have two d's. Technically, this would be a dx quantity squared, but the notation just requires a dx with a 2. Okay, so we have an option. We have our quotient rule that we could apply, or we could make this y plus 1 to the negative 1 power. It doesn't matter. They're like the same. So if you prefer to write this as y plus 1 to the negative 1, totally fine. I'll go through the process this way since it seems like most of us like that. So I'm going to have negative 1 y plus 1 to the negative 2 times the derivative of the inside, which is dy dx. Okay, what's the derivative of y plus 1? 1 dy dx. Why do we need the dy dx? Because the derivative of the inside had a y. What if the inside was a y squared? We would need a 2y dy dx at the
What
end.
if the inside was just x?
If it was x, then we wouldn't need that at the end.
If it was x plus 1, it would just be.
It would just be 1.
Okay.
But because it's a y, it's a 1 times dy dx. Okay, good? Now, I don't want a dy dx in my answer. What was dy dx? Ah. So here I have negative 1 over y plus 1 squared times 1 over y plus 1. So you're going to replace the dy dx with your previous result, right? We want to use that in order to simplify our second derivative. Yeah, now this is just, so our second derivative is negative 1 over y plus 1 to the third. Forgot my negative sign. I know, these are tricky because you actually have to use your first derivative in 2 ways. One way, you have to take this result and do that whole implicit differentiation process, and then you have to go back and plug it in at the end, and then simplify. Questions? Okay.
Wait, can you go over the last step again?
Yeah, this part? So this,
Yeah.
you're okay with this? This is
Yeah, just
negative
previous
1,
result.
negative 2 times dy dx.
Yeah.
And then dy dx we found out was 1 over y plus 1. So I'm going to replace that.
Unusable.
Yeah.
Oh, okay.
Okay, last page here. We've actually done this already, so this is just when the book kind of spells it out for you. It doesn't matter if there's rational powers, okay? Rational powers get treated the same way, like a 1/2 power, a 1/3 power, so on. So let's just, these are actually easier. This doesn't use implicit differentiation. They just had this in this chapter. What happens if you have 4x to the negative 1/2? What would dy dx be? Negative 2, x to the negative, good. So negative 2 over x to the 3/2.
Do we have, do you want to simplify like that, or is it okay if we leave the negative?
Usually I'll have something in the directions that says don't leave any negative exponents. And the reason is it's much easier for us to evaluate. Like if I gave you 8 here, we're going to want to think of that as, you know, the square root of 8 cubed and then solve that from there. Okay, for part, oh, actually, you know what? I'm going to pause here because these questions, we've actually done some of these previously, and no, it's no different than what we've already done. So I'm going to pause it. One was the first one. Okay. Yeah, so let's do this one. This one's definitely a tough one here. Yeah, we're going to do all of them. I just figured maybe I would jump around and like maybe do one, and then I'll pick and choose a couple here and there. Okay, well, let's start with one because one is actually a tough one. Usually you think they start off slow, but number one is got 2 product rules.
I don't want to do it.
All right.
Now,
Well, why don't we do this separately?
you want to do them separate? Okay.
No, what?
No, I was saying, she's saying like do x squared times y. And
Oh, okay.
are we okay if we take them apart and do them separate?
Yeah.
Don't want to like, you know, upset anyone.
I meant like
Separate each part.
Oh, this is in the recording.
Yeah, I just,
We're all friends here.
I did just start it. Okay, so let's do the derivative of x squared. 2x. We're going to keep the second part the same, which is the y. Plus, now we're going to leave the x squared times, what's the derivative of y? It's 1 dy dx. Okay, we all right on that first step? Okay, so derivative of x squared was 2x. Keep the y the same. Keep that second part the same. Plus, now I'm going to keep the x squared times, what's the derivative of y? It's dy dx. And I keep saying that over and over again. What's the derivative of y? It's dy dx. Okay, now, let's do the next part. Derivative of x is 1. Keep y squared the way it is. And then now we have keep x. Derivative of y squared is 2y dy dx. What's that? So now let's go here. Are you okay if I just write it all out? Those 2 parts? Okay, so 2xy plus x squared dy dx plus y squared plus 2xy dy dx. And derivative of 6, 0. So I'm just taking all those parts. The only thing I did was I just got rid of the 1, and I made x times 2y 2xy. Okay, now the rest, we've done the calculus. Now we have to do just the algebra to isolate the dy dx. So I would keep this term and this term, and I would move these 2 to the other side. So I'm going to leave x squared dy dx plus 2xy dy dx equals a negative y squared minus a 2xy. And don't worry if you have them switched around.
X squared.
We did that above. When we did the derivative of this part, it was 2x times y plus x squared dy dx. Keep the first part times the derivative of this. Now what? Okay, now we're going to factor out dy dx. You can.
So that like,
I'm not going to factor it out, and the reason is I don't have a common x term on the right side, so it's really not going to make any difference. You know what I mean? Like it's extra work if I were to factor that out. Because look, I could factor out a y, but I don't have a y in both of these terms. I could factor out an x on the bottom, but I don't have an x in both of those terms. So it's really not worth it to try to factor anything. Okay. Yeah, so just to warn you, this assignment will take up some space. That's the answer. That's it. That, what do you mean that's it? That was a lot. Like, we're finally done? Okay, what's the next one? It's 3.
the line's already big.
I don't like it. No, but each letter only says something.
Okay, I want to do... Now, this one actually looks worse than it is. Because well, not exactly. Okay, maybe it's not that easy. But the right side is going to be the quotient rule. However, notice the right side only has x's, so we don't have to worry about the whole dy dx thing. We only have to worry about that on the left side. So this one actually just is going to have one dy dx. So this, the right side you have to do the quotient rule, but it's not that bad. Wait, when we do that, yeah.
Do we always have to write out the ddx?
No, I just do it so you guys know that's what I'm doing. I don't usually. No. Sometimes, like with your class, I try to write out more steps. So you don't always have to write out as much as I do. I would jump right from that step to that step. I would skip that. But. Okay, so 2y dy dx, good on the left side? Okay, on the right side. Remember, these are all x's, so I don't have to worry about that whole implicit differentiation on the right side. So it's low, d high, take high, d low, cross the line, and square the low. Okay, what do we get on the top?
X plus 1 minus x.
Okay, x plus 1 minus x plus 1. So we actually get the x's are going to cancel, and we get 2 on the top. Sure? Are you just agreeing with me, or do you see how we get?
I'm sure I actually did now.
Okay. Okay, now we're going to divide by 2y. So the 2's are going to cancel. I'm just going to get y and then x plus 1 squared in the denominator. If that seemed confusing, you can also multiply by 1 over 2y and you would see, since you already have a fraction there. Yeah, dividing by 2y is the same as multiplying by 1 over 2y. Okay. Yeah, that's it. Let's see. Yeah. What's the next one? 11. The 2 canceled. Okay. And this one we want to find, is it the normal and the tangent? Is that what it says? Oh, just the slope. Okay. Okay. Okay, so we do have a little bit of chain rule here inside the implicit differentiation, but the nice thing is the derivative of the inside is just like the first one is just going to be 1. So derivative of x minus 1 squared is going to be 2 times x minus 1 to the first. And then the derivative of x minus 1 is just 1. Okay. Plus, now the derivative of y minus 1 squared. So that's going to become 2 times, keep the inside the same, y minus 1 to the first, times the derivative of the inside, dy dx. The minus 1 goes away. What's the derivative of 13? 0. Okay, I would not distribute. Here's why. The 2's are going to end up canceling. So I'm going to move this -2 and then x minus 1 over. So when I divide both sides by 2 times y minus 1, I get dy dx equals, notice the 2's will cancel. So I get -x plus 1 over y minus 1. I just distributed the minus 1. If you left the -1 out in front, that's fine. Because what am I trying to do? I'm trying to find the slope at 3/4. So plug that in. Okay, so I would like you to see, the actual homework assignment. 17, 23, 29. Is that what you guys got? -2/3? Okay. So try to see how much you can get done. You'll notice some of these here, like 31. This is just the power rule for rational. So not all of them are the really long implicit differentiation. At least then on Wednesday we can go through, we'll get all the homework done, we'll do some review, and then you won't have any homework over our short little break.
Yes!
So try to get, we don't have class tomorrow, so you'll have 2 days to try to get this assignment done. You could come see me at bonus 2 today, tomorrow. So, yes. All right, thanks guys.
These are all the homeworks.